This is the procedure for the determination of F-lab. It's an electrolysis experiment, and we'll need to take enough measurements to determine the number of coulombs during the experiment and also the number of moles of electrons transferred during the experiment. So there's a total of 9 measurements you'll need to take, so make sure you don't take down your experimental setup until you have all 9 measurements. The oxidation that occurs during the experiment is the loss of electrons by copper metal, and the reduction occurring at the cathode is the gain of electrons by hydrogen ions to create hydrogen gas. Down below I've just shown you that E cell is negative for this reaction, therefore it's non-spontaneous and electrolysis will be required. This is a rough diagram of the experimental electrolysis setup. The connections here are a little bit complicated, so we'll give you a very detailed diagram in the lab that shows you exactly how to make all the connections here, and I'll also double check it for you before you begin the experiment. So you're going to start with a large beaker, about a 400 milliliter beaker, and you're going to add 200 milliliters of distilled water to the beaker and then about 50 milliliters of 3 molar H2SO4, which will be available in the hood. Don't worry too much about getting those amounts exactly right. Could be anywhere near there, 250. Just get roughly those amounts, and that's fine. Remember, whoever's touching the acid needs to be wearing gloves, and anytime you're working with any of this equipment that's touched the acid, make sure that person who's wearing the gloves does that part of the experiment. So you mix this up. You can use a glass stirring rod in the beaker, and then you're going to fill a gas measuring tube so it's completely full. Remember, just like the determination of our lab, you can't have air bubbles in the gas measuring tube. So you fill it up completely, and then whoever's got the gloves on puts their index finger over the opening and flips it upside down into the beaker. So the opening of the gas measuring tube is about, let's say, half an inch below the level of solution in the beaker. Then you can clamp it in place, and that side of things is all set to go. But remember, air bubbles are bad, so make sure the solution's almost overflowing in the tube before you put your finger on it and flip it over. So let's come over here to the left side, and you'll see you want to dip a strip of copper metal that you found the mass of it, and you'll dip it into the solution. The copper is the anode, so electrons are being lost there during the electrolysis, and the product at the anode is Cu2+, which has a blue color, so you'll see the solution go from being colorless to more and more blue as more and more Cu2+ ions are being produced. One thing to keep in mind, the copper needs to be dipped in the solution, but the place where it's connected to the wire here needs to be outside of the solution, so make sure it doesn't fall into the solution. You can use tape to make that happen. So you'll connect the piece of copper using a wire to an ammeter, which reads the amps, and then that's connected to a power supply, and the power supply is connected with a wire to a platinum cathode, which is down here. You want to make that connection right about here outside the water. Same thing as with the copper. The connection needs to be outside the water and the solution, so you can use tape to make that happen, but make sure that does not fall into the solution during the experiment. So this piece of platinum here, it has tape on it, but the end of it is exposed. And it's the exposed end of the platinum, that's where the hydrogen gas is going to be produced during the experiment. So you want to make sure that any exposed platinum here, the platinum cathode that isn't taped up, is underneath the opening to the tube. Otherwise, hydrogen that's produced will escape, because the hydrogen is being produced right along this gray part of the drawing where the platinum's exposed. So the electrons lost by the copper are going to flow through the wire, come down the wire, and over to the cathode. where they'll come in contact with H plus ions from the sulfuric acid. The sulfate ions are just spectator ions, so those won't be involved in the net ionic equation. So when the electrons make it and come in contact with the H plus ions at the platinum cathode, hydrogen bubbles will be produced, and they'll go straight upwards, and you'll trap the hydrogen up above in the tube. So that's a rough idea of the setup. We'll talk in the lab, and I'll show you in detail how to do all those connections. But the key is to make sure all wiring is outside of the solution, except for the exposed platinum wire, which needs to be underneath the opening to the tube. So now let's discuss the calculations. There are 9 total measurements. As soon as I've checked your experimental setup, you can begin. When you turn on the power, at that moment you'll see hydrogen bubbles being produced, and at that moment you want to start timing. So you want to write down the time. You could write it down in minutes. It depends what type of equipment you have to measure the time. But ultimately, you need to know the seconds that the power is on, is what you want to know. And secondly, you want to know the amps during the experiment. So the ammeter, the amps may be fluctuating quite a bit. So what you want to do is get to about 0.5 as you turn up the power, and then keep your hand on the power knob and adjust it so that whatever your initial reading was, it doesn't have to be 0.50, it can be 0.55 or whatever. But adjust the power knob so it stays as constant as possible throughout the experiment. And as soon as you shut off the power, you can stop the clock. So those 2 measurements, seconds and amps, if you multiply them, that's going to help us get coulombs, which is one of the key things we need to get F. Now the moles of electrons, you can actually get it 2 different ways, obviously, because electrons are being lost at the anode and gained at the cathode. So method A uses the copper metal at the anode losing electrons, that half reaction, to help you get the moles of electrons. So what you need to measure is the mass of the copper before the experiment. You're going to clean it up with some steel wool and then get the mass to 0.0001 grams. Then the experiment happens, you take the copper afterwards. It's going to be wet at that point, so you rinse it with water, and then you dip it in a acetone bottle, both ends of the copper, and what that does is it gets rid of the water, replaces it with acetone, and that'll dry very quickly, so after a couple of minutes it'll be dry, and then you can take the mass of the copper after, also to 0.001 grams, 0.0001 grams I should say, and that difference before minus after is going to give you the grams of copper reacted. So if you divide by the molar mass, you'll have moles of copper, and then if you come up here, you'll see that there are 2 moles of electrons for every 1 mole of copper, so that'll help you get the moles of electrons transferred during the experiment. So we'll call that method A. So if you know coulombs and you know moles of electrons, you can divide those 2 to get the value of F. The other option is to measure the amount of hydrogen gas produced and use that to get the moles of electrons. So that's going to be method B. So things you'll need to measure having to do with the hydrogen, this should look very familiar from the determination of our lab. The gas measuring tube starts at 0 at the top, and you measure down to here the volume to the nearest 0.01 milliliters. I should mention that you turn on the power and you let it run until you have about 40 to 45 milliliters of hydrogen, and then you can stop the experiment. And you would write down, when you stop seeing bubbles, the power's off, you write down the volume to 0.01 milliliters. Measurement 6 is the temperature. You just stick a thermometer in here, get the temperature of the water to the nearest 0.2 degrees Celsius, and we can assume that's the same as the temperature of the hydrogen. This slide is actually exactly the same as the one you've seen earlier this year in the determination of our lab. This has to do with figuring out the pressure of the hydrogen gas alone. So there's a bunch of measurements here that we'll need to take to help us do that. Measurement 7 is the barometric pressure to the nearest 0.1 millimeters of mercury. Remember that this mixture of gas up here contains water vapor, not just hydrogen, so measurement 8 is to get the vapor pressure of water. And what you're going to want to do is take your temperature that you measured to the nearest 0.2 degrees, look up on the chart on the wall, and that'll give you the vapor pressure of water at that temperature in millimeters of mercury. And then, same thing as the determination of our lab, these levels here, the level in the tube and the level of the water in the beaker are going to be different. So measurement 9 is to measure that difference in height using a ruler to the nearest 0.1 millimeters of solution. And we'll talk about converting solution to mercury in the next slide. So method B, again, has to do with figuring out the moles of electrons transferred using the amount of hydrogen rather than copper. So we're going to be looking now at the cathode half reaction where hydrogen was produced. So right here I have the equation. I literally cut it and paste from the determination of our lab. You're going to take the barometric pressure in millimeters of mercury. You're going to subtract the water vapor pressure in millimeters of mercury, and you're going to subtract the height in millimeters of mercury, but remember what you measured was millimeters of solution, so be sure to divide by 13.6 before you do that subtraction. So that'll give you the pressure of hydrogen in millimeters of mercury. So if you take that, convert it to atmospheres, take the volume you measured, convert it to liters, take the temperature, convert it to kelvins, you can use the ideal gas law to figure out the moles of hydrogen. And then if you come up here, you see there's 2 moles of electrons for every 1 mole of hydrogen. So the mole ratio will give you the moles of electrons using method B. So now we're almost there. You see the Faraday is the number of coulombs divided by the number of moles of electrons. So the coulombs is the same whether you're using method A or B, but you're going to do this twice. You're going to divide the first time by the moles of electrons using the copper half reaction, and then you're going to do it again using the moles of electrons using the hydrogen half reaction. So try it both ways, see what you get for F, and then to compare those two, you're going to do the percent error to see how close each of your F values is to the accepted value. So you do the lab F value, which is what you got using your lab data, minus the accepted value, take the absolute value, so if it's negative, that difference make it positive, and then divide by the accepted value, so 96,500, and then multiply by 100%, and you will get a percent error, which hopefully will be very low, hopefully below 5% or so. So you try that using your F value from method A and your F value from method B and see which one is closer. So that's everything you need to do this lab. Good luck, and we'll see you in the lab.